Welcome to Luan's dissertation defense. The committee chair is here and all the committee members are here.
I think we can start. So, become our uh, as usual, we will delay major questions for the end. That's only questions of detail during session and interrupt you if that's okay with you.
Yes.
As your major advisor, Dr. Shed, mentioned, the committee is all here.
Oh, yeah, Dr. Prasad is online.
Checking the room. Dr. Shed is here. Dr. Van Kork is here. Dr. Ariane is here. Dr. Henson is here.
Dr. Prasad joined online.
He joined us online.
Yeah.
Okay, very good. So welcome to all, and go ahead.
Yeah. Thank you, Dr. Ashota. Good morning, everyone. Welcome to my dissertation defense. The title of my dissertation is a neurosymbolic AI approach to scene understanding in autonomous systems. My dissertation committee includes my advisor, Dr. Amit Sher, Professor of Computer Science and Engineering and the founding director of the AI Institute at USC, Dr. Marco Valtota, my committee chair, Professor of Computer Science and Engineering at USC, Dr. Vignesh Narayan, Assistant Professor of Computer Science at USC, and joining online, Dr. Krishna Prasad Tirunarayan, a Professor of Computer Science and Engineering from Wright State University, and Dr. Corey Henson, here, a lead research scientist at Bosch Center for AI. Let me start with the motivation. So let us briefly talk about autonomous systems and the perception in autonomous systems. So how do these autonomous systems perceive the world they operate in, right? So since now we are entering an era of, widespread use of self-driving cars and autonomous, robots, so it is important to take a critical look at how they perceive the world. Right now, predominantly, computer vision has been the primary tool that's been used to detect objects, and then they perform tasks like semantic segmentation and object recognition. So it is important to investigate whether the sole reliance on computer vision is enough or sufficient for the machine perception tasks in autonomous systems. So let me present you some examples. In the cases of occlusion, where a pedestrian is occluded by a large a car, and low resolution scenarios where you have inclement weather that severely degrades the visibility, and sometimes a sensor can go entirely failed, so then it would limit it would limit the reliance on any percepts that we get from that particular sensor. And of course, these are learning-based systems. There could be cases where misclassification errors can cause issues. And there are some physical limitations of the sensors. Objects can appear outside the field of view. And in the case of driving, we deal with new situations every day. So there's a good chance that the training data might have not seen the same exact novel situation. So in literature, these are referred as edge cases. My dissertation actually focuses on handling such important edge cases in machine perception tasks of autonomous systems. Let me give you a concrete example. If you are driving and then you encounter this kind of a scene, so what would you do? What would you expect to do? So you can see that there's a bowl on the road and there are a couple of parked cars. And from the looks of it, it's like a nice residential neighborhood, right? Then as a human, since we have an innate understanding of how the world works, we would assume that, okay, there could be a child following that boat. But if you think, take a step back and think for a moment, how would a computer vision handle this? There's no visual cue of a child in this particular scene. So that information is currently out of scope. So in this regard, what my dissertation proposes is to take the full benefit of the computer vision and empower it with the background knowledge so we can handle these kind of edge cases. For example, if there's a way for us to infer that from the ball that is being detected, children play with toys and children live in residential neighborhoods. So by using these kind of relational knowledge, if we could infer that there could be a possibility of seeing a child in the scene, that's where we want to go. So this dissertation proposes a novel perspective for scene understanding that is based on neurosymbolic AI. This is my thesis statement. Effectively understanding scenes requires a unified representation of scene data and background knowledge. A neurosymbolic AI approach to scene understanding leverages such a unified representation to enable advanced expression, inference, and labeling of scenes, improving the perception of autonomous systems. This vision is realized through several contributions. My dissertation has 5 concrete contributions. The first one is a representation, where we look at what is the best way to represent scenes. Second, we look at, once we have a good scene representation, how could we have the semantic information that we have in that representation also retained in the latent embedding space. Third, we look at a novel inference task called entity prediction, which I'll be explaining in the later slides. Fourth, we looked at unobserved entity labeling, where we focus on existing data sets from the autonomous systems domain, and how could we enrich them with labels for unobserved entities. Fifth, we look at a novel benchmark that is on cognitive visual reasoning. These are the publications that cover the 5 contributions listed here. During my proposal, I explained in details the first 3 contributions. So today I'll be spending less time on the first 3 and focus more on the last 2. Okay. In today's talk, I have divided it into 2 parts. The first part, I'll be talking about the 5 contributions. On the second part, I'll be briefly talking about some of the industrial applications and the broad impact of my research. Okay, let's start with the first research question. Representation, what is the better approach to represent scenes in autonomous systems? If you look at the literature on how people represent scenes, so the end-to-end learning algorithms, like deep learning algorithms, they can directly consume the raw data, like semantic, low-level 2D or 3D images, and then perform downstream tasks. And if you want a little bit more richer semantics, we can, of course, have a scene graph generation. So the scene graphs do capture the local context that you can visually see from the scene. And in a special case, if you want to represent just a singular dimension, for example, spatial relations, such as the ego vehicle is on the right side of car 0. So there are spatial graphs that only focus on the spatial relations. So in our pursuit for a better representation, we came up with sort of a checklist. So a better representation should be able to represent the heterogeneous data, because in the autonomous systems domain, we deal with sensors, cameras, LiDAR images, so lots of heterogeneous data. And we want to be able to represent both the local context as well as the global context. We also want to represent more than one scene dimension. For example, we want to have the time represented along with the spatial relations. And this representation should be able to integrate easily with existing deep learning algorithms. So the knowledge graphs, they tick all these boxes. In addition to this, they also adhere to FAIR principles like findability, accessibility, interoperability, and the reusability. Next, I'll briefly discuss how did we construct scene knowledge graphs. The first step is have an ontology. So we are basing our ontology on this scene ontology, which is developed in-house at Bosch. That is a basic structure to represent any scene. It doesn't have to be from autonomous driving, autonomous systems domain. So to create a sort of a dataset agnostic ontology for the driving domain, what we did was we looked at a couple of open, publicly available datasets And then we gathered what are the important, concepts and relations for driving. So the driving scenes ontology we created contains about 113 classes and 10 object properties. Now that we have an ontology, the second step is to create a knowledge graph. So we looked at a couple of high quality data sets like PandaSet and the new scenes. So at the time of knowledge graph instantiation, what we do is we take a scene from a data set. So in this particular scene on your left, there are two objects, one parked car and one pedestrian. So what we do here is we create new instances for each detected object. And then we link them to their corresponding classes in the ontology I just described. We also do one thing here. Since we want to have a richer representation, we represent any available metadata. For example, if the time is present, we represent the time. If the GPS coordinates are present, we represent them as location attributes. So we follow this process for all the available scenes. So what you see here is some brief statistics about the two knowledge graphs that we developed from PandaSet, and the other data set is called new scenes. There are large knowledge graphs. For example, the new scenes contains about 6.2 million triples, PandaSet 3.3 million triples. And on your right, what you have is the entity frequency. So since these are real world data, so you can see that the entity frequency follow a long tail distribution, whereas there are some entities naturally occur in low frequency than others. Then, since as a benefit of having a knowledge graph, we can easily integrate external knowledge. So we did focus on two types of external knowledge integration. First, we looked at integrating geospatial knowledge. So in autonomous driving datasets, usually the location is represented as a GPS point, such as like latitude or longitude. So we wanted to enrich this information with more semantic or location relevant location attributes. So for that, what we did was we did a reverse lookup of that lat long information on the OpenStreetMaps. And then we gathered as many location attributes as possible. For example, in this particular case, this is a scene from a highway. It has 3 lanes and the speed limit of 30. This enrichment did increase the entity classes by 34% and overall triples by 3.19%. Second, we looked at common sense knowledge integration. So for this, we looked at 4 common sense knowledge resources, and we added a new triple such as like pedicab is conceptually related to a bicycle. Pedestrians are more susceptible than cars. So these types of common sense relation we gathered from these resources and then added to our graph. So overall, we added about 7,200 common sense relations. So as a quick takeaway for this, the first contribution, we made the case that the knowledge graphs are a better fit to represent, scene in the autonomous systems. And we constructed a data set agnostic ontology, constructed 2 large knowledge graphs from real world driving data. And we also demonstrated external knowledge integration focusing on geospatial as well as the common sense knowledge. Okay. Let's move on to the second contribution, which is the expression of scene knowledge. Here, what we are focusing on is, so how to make the underlying knowledge representation expressive in the latent space. So traditionally, when people build knowledge graphs, they're actually not built for deep learning applications. They are built for inferencing tasks. So you have a knowledge graph, then you would use a reasoner like OWL Reasoner, then you would do Sparkle querying. So if you have a downstream application that relies on knowledge graph information, then you would directly use that. But now that we are seeing an increase, increasingly people are using knowledge graphs with deep learning algorithms. So we were trying to think what are the structural differences that we have to make it better suited for deep learning applications. So we looked at a literature, how people often, evaluate these knowledge graph embeddings. So it could be either through benchmark tasks like link prediction or entity classification, or people can directly use it with the, for example, like recommendation use case and see whether the inclusion of knowledge graph did improve the results. Or some researchers take another route. They would do intrinsic, evaluation. So there are some metrics proposed for like, quantifying the relational aspect, quantifying the hierarchical aspect. So in this background, what we did was we were basically looking at what are the different ways that we can uh, change the structure of the knowledge graph so it would make the latent space more expressive. So this is the vanilla knowledge graph. That means that once you create a knowledge graph, this is how it would look. Then we created two more variants. The first variant, what we did was we made the implicit typing information explicit. In the third variant, what we did was, in addition to the typing information, we also made the graph patterns, for example, paths, explicit in the knowledge graph. So we do these sort of pre-processings before we learn any embeddings. You can see here the effects of our effort. So on your left, what you have is a vanilla, the 2D projection of the embeddings of the vanilla knowledge graph. And on your right, what you have is the embeddings generated from the enriched graph with graph patterns. You can see it now understands the concept of frame scenes and the sequence scenes, which is sequence scene is basically a video, and frame scene is basically a frame that you sample from that video. Second, we also did look at how it would help identify the entity, like part of relations. For example, if the instances of cars are clustered together with vehicles, because they are all vehicles in the ontology. We saw that this process actually did improve the expressivity of the scenes in the latent space. And as a quick takeaway, if you have a knowledge graph with highest levels of informational details that yield better quality embeddings, hence leading to higher expressivity. Third contribution of my dissertation is inference task, where we focused on how to leverage the relational knowledge in scene graphs for entity prediction. I'm using the same example that I showed you at the very first slides. Seeing a ball on the road and then predicting whether there could be a child following that ball. So the KEP is the task of predicting the inclusion of such potential entities in a scene, given the current and the background knowledge of the scene is represented as a knowledge graph. So we hypothesized that we could predict such entities through the use of knowledge graphs to provide this expressive, holistic representation of scene knowledge, and the application of neurosymbolic KI for the knowledge completion. Before I actually introduce the solution that we developed, let me give you a quick primer on link prediction, because our solution is actually based on link prediction. So link prediction is a well-studied problem in the semantic community, because when we build a knowledge graph, it is impossible for us to build a knowledge graph that is complete. So that it is assumed that the knowledge graph that you build are inherently incomplete. So the link prediction task is being used to enrich the graph with missing links. So traditionally, there are different, structure-based algorithms that were used for link prediction, but now people are using machine learning-based or deep learning-based algorithms. So the traditional setup is you take the graph and you treat all the triples that you have in the graph as positives. And then as the next step, you corrupt these triples to create random negatives. And then you learn a machine learning model where you would prefer seeing the positive data or positive triples over negatives. So once you do this learning procedure for all the training data that you have in the graph, you end up with an embedding space that is capable of inferring the missing pieces of information from the triples. So we use the same idea here. This is a subgraph from our knowledge graph. Assume that we mask E2 and E4. We consider them as test data. And then we take all the training data when we use knowledge graph embedding algorithms to transform the graph into an embedding space. And then we do link prediction to predict the masked entities. But there's one caveat here. In traditional link prediction, you assume that there's a direct link that you want to predict. So the link prediction only works on direct links. But if you look at our graph, we are actually, we want to predict the classes. We don't want to predict, scene could include a parked car 1. But we want to see whether there's a parked car, whether there's a child, not the child. There's a child in the scene. So to make it possible, what we did was we introduced a reification rule. So you would reify the path that exists between the class information and the scene through a direct link. Now that you have that direct link in the scene, you can still reuse any of the link prediction algorithms. Based on the analysis, the evaluation that we did on 2 knowledge graph versions that we have created, we can see that this method is effective in predicting missing entities with 0.87 peak hits at 1 value. So in this contribution, we looked at a novel problem formulation, knowledge-based entity prediction, and we evaluated it using 2 real-world data sets and demonstrated that this is effective in identifying missing entities with a peak performance of 0.87 hits at 1. Okay. Next, let me move on to the 4th contribution, which is labeling of unobserved scenes. So here, what we are focusing on is how to augment the existing autonomous driving datasets or datasets from the autonomous systems with labels for unobserved entities. So I already made the case early on that due to these situations like occlusion, degrading weather, the sensor failures, and objects appearing in the outside field of view, and dealing with these new situations, so it is we can safely assume that if we collected a real-world data set, they could contain unobserved entities because of these issues. So let's say that we take a high-quality, even human-annotated autonomous driving data set, and we won't use that to train my self-driving car. But the issue is, if the data that I rely on does contain the unobserved entities, then whatever the learning that I expect to have is incomplete. So here, what we are, in fact, actually, we did take a look at one of the data sets here. We found out that about 12.5%, 12.49% of the scenes are incomplete with at least one unobserved entity. So the research question is, if you are given such high-quality data sets, how would you augment them with labels for unobserved entities? So I want to make a quick comparison between the label augmentation with the data augmentation, because that can be easily confused. So traditionally in machine learning, if you don't have enough data, so what you do is you augment the data set. So the process is you take a data point and you apply some transformations. So you end up with multiple variations of the same variations of the data point. So you would grow the data set size. But when I say label augmentation, it doesn't mean to grow the data set byte size in terms of the data points. Instead, what I mean here is that if we have a data set like this, let's say that we have a scene, the original labels are given as like L1 and L2. We want to see whether we can improve the number of labels per scene. So we would grow the label space instead of the number of data points. Our solution for this problem is based on a well-studied psychology theory. It's called Apache's object permanence. So this is actually a very commonly used with a game called like Peekaboo. You play with babies around 1 to 2 years of age, because we humans do gain that understanding around that around 1 to 2 years of age. So if you show a ball to a baby and then you cover it with a large object, then they would learn this ability that the ball didn't just disappear in thin air. It just that you can't see, but the ball is still there. So the concept of object permanence is also used in basic formal ontology when they talk about the continuance. So we wanted to apply this object continuance in the, for example, in the driving domain. Let's say at timestamp t, there's a pedestrian currently occluded by a parked car. So the car in the middle doesn't see the pedestrian. But that doesn't mean that the pedestrian does not exist in that scene, right? Similar to the Peekaboo example. Even though the ball is not visually appearing in the scene, the ball is there. It's currently occluded. So by the time of t plus 1, then the person slowly starts walking in front of the car. So at that point, you can see the person. So we thought about it as a like a sequential process. So if you arrange your scenes in a sequential manner by time, then is there a way that we can inspect the context of, let's say, a particular target scene and then infer the possibility of detecting such currently unlabeled or unobserved entities? The solution that we came up with is a simple deterministic process. So what we do is we pick a target scene, and then based on the target scene that we pick, we first gather all the entities that are currently observed. So this ET is basically the set of entities that are currently observed in the scene. Then we define the context in terms of the past window as well as the future window. So the window size is a tunable hyperparameter here. We gather all the entities that are observed in the past window as well as the future window. And then see, is there any entity that is currently not observed in the target scene, but did observe in either of the past or the future window? If that is the case, we include those entities back, we integrate those entities back to the target scene. So we applied this process for the same two data sets that we have been using, the Panda set and the new scenes. As you can see, we did improve the percentage of incomplete frame scenes by 12.49%, meaning that we found 12.49% of frame scenes with at least one unobserved entity. And in the case of new scenes, it was actually much higher, about 38.51% of scenes with at least one unobserved entity. And if you look at the last row, the entities per frame scene, we see about 8.24% improvement with respect to Panda set and about 18.5% improvement with respect to new scenes. On your right, what you have is an example from a Panda set. So currently, the data set has one label, which is in this scene, which is car, right? After applying CLUE or the context-based labeling of unobserved entities algorithm, we were able to find the two new labels like person with object and person sitting within the context. So how that happens is that there's a person in the parked car. In a couple of seconds later, the person is trying to get out of the car. At that point, the computation algorithms did pick up those changes and labeled person with object and person sitting. So now that we do investigate or analyze the context of both future and the past windows, we were able to gather that, okay, these are the new two new annotations that we have to include with the target scene. Then we did perform a further analysis on the augmentations. So as I mentioned, the window size is a tunable hyperparameter here. So we did three types of hyperparameter changes. For example, we only looked at the future scenes. We only looked at the past scenes, and then we considered both future and the for both past and the future windows. And then we changed the window size from, let's say, in the panda set from 5 to 20, and in the new scenes from 1 to 18. So the objective here was to find an optimal configuration that yields the highest number of new entities, new unobserved entities with respect to a data set. Then we also looked at the augmentations with respect to entity types. So as I have mentioned earlier, we are not dealing with simulated data. So the real world data sets, they basically capture what you see on the road. So for example, you wouldn't see, the wheelchairs, the ambulances, not so much compared to, regular cars or pedestrians, right? So we were trying to see when we improve the labeling space with this method, how would these new labels that we find through Clue method improve across these different entity types? So one interesting observation that we saw here was when it comes to entities that naturally occur in low frequencies, this particular method tend to work well. So the percentage improvement with respect to those entities that occur in lower frequencies is significant here. Then after we did that analysis, we also wanted to see how do we evaluate these labels? Because so someone can argue that, okay, now you have come up with a set of new labels, but how would you guarantee that the labels that you came up with are actually correct? Because we know that this is a deterministic algorithm. So, there's no learning happening here. So whatever we gather are actually based on what you see in the context, right? But still, there could be a chance that we may be adding false positives, right? So one alternative is we take a couple of human annotators and give them the task. So can you please look at the context windows and visually see those unobserved entities? So they can verify, right? But then we actually thought in terms of the frame rate as well as the number of scenes that they have to look at, right? Let's say if you take new scenes with the window size of 90, and we consider both past and the future window. So in this particular case, if we are to ask a human would have to look at 228 images, meaning there are 6 camera angles. There are 19, they are put like 38 frames, and then you have to look at each and every image to detect these additional labels. So this is not feasible because we have about in the case of Panda set, we have more than 8,000 frame scenes. So this is not feasible. So then what would be an alternative approach? So how would you still verify that the labels that you predicted or inferred are in fact true? So we thought about this problem. What we did was an evaluation through a proxy. So let me give a quick recap because we are using the same evaluation setup with a slight change. So when I talked about the entity prediction, right, the knowledge-based entity prediction, I talked about the masking-based evaluation. So we split the data set into training and testing. We learn embeddings from the train split, and then we report the performance on the test set. So
Ruan, sorry to interrupt. This is Michael Hunes. I was just wondering if I could ask for a clarification about something a couple of slides ago. You don't have to go back there, but it has to do with the object permanence. And so if an object is occluded, if it's temporary, then you might assume that the object did not go away, as you've described. But that, of course, depends on time. So if it's a tenth of a second, a pedestrian will still be there. If it's 1 year, a pedestrian won't. And so I presume that that's where the window size comes in. Is that correct?
Yes.
Okay. And so, the number of frames you're looking at is a few frames. It's not a year's worth of frames.
Yes, that is exactly true. So in this case, Dr. Hunes, the data set that we deal with. So in one particular case, we have a frame. We have 40 frames per minute. So in the other case, we have 20 frames per minute. So when we defined the window we wanted to look at, so this actually less than 1 minute long windows. So yes, you are right. So we basically, since we are arranging the scenes based on the time, and we only look at a couple of milliseconds before and after.
Yeah, perfect. And the second part is, can this, the sort of window size that you're choosing for the permanence, do you make it different for different entities? Was that what the subsequent slide was about? So some things
not really.
might disappear faster than others. And so if it's, a dog is fast, it can run away and might not still be there. A human in a wheelchair might be very slow and so might still persist. And so I guess that's a consideration. You could make the length of that persistence assumption different for different entities.
Okay. So the results that I showed you, the analysis that I showed you, we did not change the hyperparameter based on the entity type. That figure was about we consider, we globally consider the window size, and based on, let's say, if we pick the window size of 19, and then we came up with the new entities, new unobserved entities per scene. We were trying to now see, based on these new additions, what are the percentage improvement with respect to each entity type. But we have not.
That's clear.
Yeah, we have not looked at. Yes, we
have not looked at. Thank you very much.
Yeah, thank you.
Yeah.
Okay, so coming back to this slide, so as I was mentioning, a quick recap: during the standard KEP evaluation, we split the data set into 2 parts, and then we trained the embeddings and then tested on the holdout. So here, what we thought was, in KEP, we already saw, given the background knowledge or the knowledge graph, we can predict new entities, right? We can predict entities, but we evaluated using a masking-based approach. So what if we consider that KEP process to be an annotator, to an independent annotator? So in that case, we have to make a slight difference here. So since we are interested in predicting totally new set of entities that are not observed currently. So we learn the embedding models on the full data set. And then during the inference time, we ask the model to generate a new set of entities. So now, as I said, we are treating this as a new, another annotator, right? So we have the clue method, which is the context-based deterministic method to generate some labels. Then we have an alternative method, which is learning-based that leverages the structure of the knowledge graph to predict new entities. So we treat them as two separate annotators. And then we computed Cohen's kappa to quantify the inter-annotator agreement. So as you can see, we did look up multiple knowledge graph embedding algorithms. For example, the Transy, complex, Distmalt, Tucker, Holy, and the Rotate. In the case of Rotate, we have seen that the inter-annotator agreement between the entity prediction model and the clue is significant because it is over 0.6%, 61%. So as quick takeaway, we proposed a context-driven deterministic method for labeling entities that are likely unobserved, thus missing in existing data sets. So we did validate this approach on two real-world data sets, PandaSet and NewScenes. We also report that we can expect the improvements of like 12.49% with respect to PandaSet and 38.51% with respect to NewScenes to recover at least one unobserved entity. And as I mentioned a couple of slides earlier, that the further analysis did shed some light on this method's ability to predict or infer these rare long-tail entities that are naturally occurring in low frequency. Okay. Now, the fifth contribution is a benchmark. So in this particular work, what we are focusing on is, to what extent can AI models perform cognitive visual reasoning over perceptually incomplete real-world scenes? So to give a little bit of background, if you look up, visual reasoning benchmarks, there are a bunch of visual reasoning benchmarks. For example, if you take a model like a benchmark like Visual Logic, so you are given a visual sort of like a pattern matching sort of puzzle. So there are certain puzzles, then there's a one question mark in one tile. So you are expect to look at the puzzle and then understand the pattern and then predict, okay, this could be the next pattern that I expect. And there are certain math-related benchmarks, like vision benchmarks. So in those benchmarks, what happens is you are given a geometric problem. So you have either grade school or SAT-like competition, so Olympiad math. So you have these geometric problems and the textual description of the problem. And then you are expected to solve it. So you basically, over the past couple of years, we have seen, teams would compete on these benchmark tasks, coming up with new models, new foundation models. Then there are also visual question answering, like very popular visual question answering benchmarks. So the types of data that you see in these benchmarks is, so let's say, for example, you are given this image of a pizza. Then the benchmark would have a textual component asking how many slices of pizza are there. Is this a vegetarian pizza? By looking at the image and analyzing the ingredients, the models are expected to answer these types of questions. So throughout my presentation, I have been talking about like edge cases, partial occlusions, reasoning over incomplete scenes, right? So we have been thinking when we look at these kind of benchmarks. So we are dealing with sort of a unique problem setup. We assume that the visual information we have is incomplete. So in our case, we deal with these kind of real scenes that you assume that there's something missing. So we try to see what if we consider that as a novel benchmark task, because in the background of all the other benchmarks for visual and cognitive visual reasoning, we thought this is an interesting take because we can assess whether the different types of algorithms, like say foundation models, the vision language models, are they capable of handling reasoning over incomplete information? So we did try to compare our benchmark, which we call as the Q-bench, against these different varieties of the benchmarks that I presented. So they all have multimodal data, and for example, VQA has real scenes. Others are like diagrams taken from like visual diagrams of geometric problems. Then one unique thing here that the other benchmarks didn't have is we assume the perceptual incompleteness. So next, what we did was, since this is a new benchmark, we have to come up with different types of solutions. First, we have to show that how capable are current AI models in handling this task. So we developed three types of solutions based on different classes of algorithms. The first one, you're all familiar because this is basically the KEP process, the knowledge-based entity prediction. Here we expect the input to be a knowledge graph of scenes. And the models that we typically deal with here are all knowledge graph embedding algorithms like Transy, Holly, and the ConvKP. And the inference task looks like once you train an embedding space from the knowledge graph, you infer to complete triples of this kind, like scene includes type, the class. So the output is basically top K like rank list of entities, so we can see whether the model is capable of predicting the task at the very top. Then we developed solutions based on foundation models. First, we looked at the large language models. So one thing about the real world data that we deal with. So in most cases, you don't have like textual description of the scenes. So right now, what we have done was we go with the sort of a text template. We describe briefly what is currently observed in the scene. Then we do use like large language models like Gemma, Qwen, Llama, and Mistral. So a family of algorithms, family of large language models, and then report the zero-shot performance on predicting these missing entities. So we ask the models like, based on the information that is given, predict the entities from most likely to least likely. So we can take the top K there as well. We also did the same with the multi-model large language models. So here the input is textual description of the scene as well as the visual images that we have from the data sets. So we used like Llama 3.2 Vision, Instruct, and Intern VL3, and Qwen VL. So we do the similar, yes. So, okay, that's a good question. So the incomplete, what I mean by incompleteness is as I explained earlier with respect to clue, right? So if you see a ball on the road, then you don't see a child. Currently, if you take the scene as a whole, you only rely on the current observations. And you assume, in this case, we don't assume that current observations are everything that is there. So we assume that there could be some more that is currently not detected and labeled in the scene. So the objective here is, if we assume the scenes are, so object detection and the recognition is incomplete, how could these different solutions, different classes of algorithms infer those missing entities? That's what I mean by.
Just to kind of dig a little deeper.
Mm-hmm.
I can take an image.
Mm-hmm. Mm-hmm. Yeah. Okay. Yeah. Yeah. One I show. So perception can actually also contribute. So in this line, actually quantify this in the same way, assume that it is incomplete the conceptual. So quick clarification, none of the scenes that we are using, they are AI generated. They are all real world scenes captured by, so one is PandaSet, is from Scale AI. These are real world scenes. Basically, people drive cars with 60 degrees of freedom cameras, and then all the data sets that I deal with in my dissertation, these are real scenes. To answer the second part of the question, quantification, there's no way to directly quantify how much of the entities actually you are missing. It is generally assumed that due to the perception failures, because there could be a case, for example, let's take occlusion, right? If a pedestrian is occluded by a large truck, in that case, we don't know how many pedestrians are behind that large truck. So it is assumed that in these real world, driving scenes, there could be entities that are currently not detected, hence labeled in the scenes.
Just for clarification,
yeah.
If I understand correctly, when there is a ball, the chance that there is a child around who can come on the road is very relevant, and you wanted to capture that.
Yeah.
That is the incompleteness in the scene you are looking at, but the child is around.
Yeah.
When there is a driver sitting on the road side, there is a chance that come up. And then completing the incomplete information that person was identified. And this is human judgment that this is relevant or not relevant. Yes. And those are the human judgments where they could be relevant to the scene processing which you have captured.
That's right. That's right. Okay.
I hope that.
Yeah. Thank you. Then we introduced two types of evaluations. The first one is the masking-based approach, which we have done earlier. We basically mask out a couple of entities and then try to evaluate whether the models are able to infer the masked entities. The second type is the real unobserved entity prediction, where we assume the scenes are incomplete. Then how do we evaluate those? We basically take the labels that are provided by the clue, we consider them as goal labels. These are the benchmark results. As you can see, when we did the masking-based evaluation, the link prediction-based solutions did score high compared to LLMs and the multimodal large language models, achieving like 0.87 exact one. And when we did evaluate it on the real unobserved entity prediction, we see that this task is inherently hard. Even for the link prediction models, we achieve about like 0.316 exact one. But the LLMs and the multimodal language models are really struggling in this particular case. As quick takeaways, we propose this novel benchmark for cognitive visual reasoning that targets the inference over perceptually incomplete scenes. And we developed three types of solutions from three different classes of algorithms. And then we propose two ways of evaluating this benchmark, masking-based and real unobserved entities. For the benchmark, we did a comprehensive evaluation across 11 models from the three algorithm classes. And our benchmark results lead to the conclusion that the neurosymbolic method, which is the link prediction solution that we have, tend to work well compared to the LLMs or the VLMs here. Okay, now that I have covered the 5 contributions of my dissertation, next I would briefly go over some industrial applications and the broad impact. First, we made the knowledge graph, a suite of knowledge graph that we built publicly available. And we are happy to see that other researchers are using this resource. For example, one of my colleagues who defended last week. She was using this for understanding causality and the root cause analysis. And one example I thought of sharing here was the cross-model retrieval. So this was a paper by one of the largest automakers in China called Li Auto. So they are using this knowledge graph for cross-model retrieval. So the cross-model retrieval is you are given, let's say, the query in text. Give me the scenes of accidents. And the task is to retrieve scene data, either images or videos, based on the query that we have given. So how they're using our knowledge graph is they argue the case that when it comes to these real world scenes and complex queries, so it is hard to understand what the user meant, what is user's intention, and what do they mean by like pedestrians. So you can use, of course, a large language model to provide the textual embeddings of the concepts, but they want to have something that can provide the global context. So they use our knowledge graph. They basically first transform that into embeddings and then use it in conjunction with the textual embeddings, and then report that the use of this knowledge graph for the cross-model retrieval did yield better performance. The second, I want to briefly share how this research led us to totally a new set of problems that we handled in Industry 4.0. So from the very beginning, I have been focusing on these edge case scenarios in driving, right? Then I owe it to my advisor, Dr. Sheth, a couple of years back when we had the opportunity to write a proposal for the manufacturing. So we were thinking of, okay, we have looked at, driving scenes and the edge cases. So how about we see a practical application in the, manufacturing? So what we thought was, if we are to see manufacturing cell as manufacturing scenes, the same way that we have seen the driving scenes, then there are some rare exceptions and anomalies that occur at a very low frequency that could also, similar to the edge cases, that could also cause like catastrophic failures, right? So these rare events are very frequent occurrences defined by the spatial, temporal, and semantic context. For example, equipment failures, quality defects. These are the anomalies. And the industries like automotive, they lose about 2 million an hour and 50 billion annually because of these rare events. So we proposed this idea, and I had the opportunity to collaborate on multiple papers and multiple projects in this line of work. First, when we started, we couldn't find any good resource that we can look up for the rare events. So the first thing we did was we spent quite amount of time to lay the foundation. Basically, what are the different ways that you can evaluate these rare events? What are the different computational methods that we can use to do rare event prediction? This is a ASEAN Computing Service survey that we have published. And then the other selected outcome is we also did look up how to improve the rare event prediction through data enrichment. Here we basically looked up if we have a real world data set, not simulated ones. So how would you enrich the data in a way that yields a better performance? We also conducted recently a tutorial on the same topic at AAAI this year. Then I wanted to briefly share my PhD journey. So over the past couple of years, I have quoted over 25 publications in 7 journals, for example, ASEAN Computing Surveys, and 17 conference, symposium, and workshops in places like AAAI, ACL, ESEL, and ISWC, and also a book chapter at iOS Press. I had the pleasure of working with a bunch of collaborators and presented, organized and present 5 tutorials at AAAI, IEEE Big Data, ISWC, ACM Hypertext, and US2 TS. Also, I have collaborated with Bosch for 4 years, 3 summer research internships, and Bosch graciously gave us 50K to support my research. And then this collaboration yielded about like 10 plus research outcomes and 3 of patent spending. Over the years, I have contributed to writing of more than 5 NSF grants. So one particular example is the one that I showed with respect to manufacturing, where I worked as the lead student contributor. I have had the privilege of also mentoring bright students from, I think, the whole spectrum, like high school to bachelor's, masters, and PhDs. I collaborated and mentored on several different topics that are not related to my PhD. So this mentoring process actually yielded 6 joint publications and 3 poster presentations and 1 tutorial. When it comes to academic and volunteer services, I have had the opportunity to work as, serve as the program committee member at IJCAI, ISWC, the web conference, and the knowledge increased learning, and reviewer for multiple top venues like AAAI, ACL, CIKM. And I also did work as a student volunteer for Calling 2025 this year at Abu Dhabi, ISWC, ACL 2023, and AAAI 2020. This is sort of a, dissertation contributions at a glance. First, we looked at a unified representation of scenes. We came up with this dataset agnostic ontology and a couple of knowledge graphs to represent driving scenes. Then we did study the expressivity in scene knowledge, and we showed that if you have a higher informational detail, that yield better quality embeddings. Third, we introduced a novel problem formulation called the knowledge-based entity prediction to predict the entities in driving scenes. And we reported that the solution that we came up with is able to predict entities with high precision. Fourth, we introduced this clue context-based labeling method for labeling unobserved entities and showed its effectiveness across 2 data sets. Finally, in the 5th contribution, we proposed a novel benchmark for cognitive visual reasoning and compared 11 models across 3 algorithm classes. All this work would have not been possible without the help of a lot of people. First, I want to thank my dissertation committee, starting with Dr. Sheth. So from the very early on, when I joined Dr. Sheth's team, I wanted a research career after PhD. So I want to thank him for giving me lots of opportunities to grow as a researcher, involving me in proposals, keynotes, reviewing, lots of different opportunities for me to grow as an independent researcher. Then I want to thank Dr. Henson. So when I first started my internship in 2019, I had no idea about autonomous driving, knowledge graphs. I developed my first knowledge graph with him. I wrote my first research paper in my dissertation with him, wrote my first patent with him. So you have been an incredible mentor, and thank you for everything, Corey. Third, I want to thank Dr. Prasad. So those who graduated before me during Noesis, they would say that you can go to Dr. Prasad and talk about your research. He would stop everything and listen to you as if he was listening to you for the first time. I have not seen anyone that is so much invested in learning more about your research, and always try to ground us in years old research that we may have not heard of. So thank you, Dr. Prasad, for always being always being a very good reviewer and always helping us learn new things. I also want to thank Dr. Marco Altota and Dr. Vignesh Narayanan for always helping me with identifying the scope. What should I focus on? What should I give the higher priority to? And also with respect to all the documentations and official requirements. I also want to thank all my co-authors and collaborators. None of the works that I have done would have been possible without the help of those bunch of bright, good people. And I also want to thank the funding agencies. I benefited from 2 NSF grants, and also want to thank Bosch. I had 3 internships and the financial support from Bosch. I also want to thank all of you, my colleagues at AISC. When we first moved here 2019, then briefly after 1 semester, COVID hit. So we went through a pandemic, a lot of uncertain times. Thank you for being there. We had so much fun. The best group I could ever ask for. Then I also want to thank my family, my father, mother, and my sister for always trusting me, and especially my parents for teaching like very early on the value of education. Then my extended family, my father-in-law, mother-in-law, and my brother-in-law for always be there for me. And last but not least, I want to thank my wife and my daughter for constantly reminding me what is important in life. Yeah. Thank you. And these are the resources, the DC in KG that is publicly available, and a bunch of papers. Yeah. If you have any questions, I'll be happy to answer.
Thank you for the excellent presentation. Accept some questions from the board online. Questions. All this. Because you were under meeting just in. So, yes.
Mm-hmm. Mm-hmm.
When you say the description of the image, I'm curious to know how you feel this description.
Okay, that's a good question. So right now, we are using a very simple template. So we did look up literature in that regard. You're right. You can, so the one approach is you take another LLM that you're not using for the testing, then ask that LLM to generate the textual description for you, and then use it with other LLMs. So what we did was, since we basically know how to describe the scene well, we came up with a template. So with respect to each frame, we would replace the objects that are currently observed with respect to each frame, and we basically replace those variables in the template. Yeah. Yes. That's right. Yeah.
So you say context.
So that's a good question. The results that I reported, we have not asked. We made it very clear. So we basically want the LLM to just give a rank list of entities. So yes, that's right. Yes.
I think one way. So your objects in the future.
Mm-hmm.
So one very important problem is the data is like
yeah.
Right? So it's the
mm-hmm.
But can you tell something that I can't pick off my data obviously or the
So when we studied the clue problem, right? So there are multiple different reasons why we are left with unobserved entities. Noise is one of them. So we have not investigated with respect to each of these categories right now. Yes. So yes, we have not looked at noise particularly here. Yeah. Thank you.
Fortunately, I don't see the online chat. Do you see any questions from the chat? Maybe someone else.
No, I don't see any questions. No. Hi, Dr. Prasad.
Okay, let me ask you a question. So I think for a long time we have done this perception cycle and integration of abduction and deduction. And I did not see an explicit mention of all that in some of your formulation. And I think I have a general idea of why that's the case, but anyway, I just want to get your take on it. So let's start from your example about so let's start from your example about the ball in the scene. And the hidden entity appears to be the kid that's hidden from us. So when I think about that in the broader framework, right? So the existence of ball seems to be explained by the presence of this quote unquote cause. So did you explore formulating that in the broader perception cycle setting and trying to look for these entities through the idea of focus and but I do see that in that formulation you won't be able to easily find these hidden entities through just the visual inspection. But I just wanted your take on was this general framework not useful for other situations?
That's a very good question, Dr. Prasad. So in our formalization, we did not dig deep into the abduction or the deduction reasoning. So since we are using knowledge graph and then using embeddings to infer the entities, right? So you are right. So we may be implicitly using the correlations because if a particular object correlates more with another object, then there's a likelihood that that correlation did help predict that. So I think it's a good idea that we should invest more time, we give more thought into that. But in the right formalization, we have not specifically looked at those two separately. We considered reasoning as a general reasoning problem. Yeah.
And I have a separate comment, and I think your talk covered it later and did explicitly connect it. So I just want to make that point. So, for example, every object in the scene, right, has a reason to be there. So you just picked on the ball and said, okay, I'm going to investigate, say, a kid on the thing. But if you see a car, yeah, it is there because somebody parked it. There is a tree because somebody planted it, right? So why did you focus on just the ball? And that's because it is somehow anomalous in some sense. And so there is the issue of temporal aspect that was also referred to earlier by Dr. Huhn. So we may want to consider like the static versus dynamic issues and see if that enables us to decouple and better justify why focus on some objects versus others.
Yeah, that's also a very good point. I think there are a lot more to do here. So one interesting thing we also thought along the same lines is how do we evaluate the predictions with respect to certain entity types. For example, the ball, right? So then I think we can answer these type of questions like we expand on the granularity. Right now we are considering as a general prediction problem, but there are a lot of follow-up work that we can do to investigate and dig deeper, when it comes to individual entity classes. How would this kind of framework help predict those entities? So yes, I agree. There are a lot more to explore here. Yeah. Thank you.
Yeah, if I may follow up on my question to you. Yeah. Another way of thinking about it is I'm using any kind of explicit modeling besides the knowledge itself or the choice of entities. So in particular, any kind of prior information as to what you would expect to be in a scene.
Okay.
So to me, it seems like your approach is very much data-based. The information is just the structural information represented in ontology. But maybe as you apply your techniques implicitly, you're building a model. I don't know whether you could elaborate.
So one interesting thing is, because we are using knowledge graphs. So similar to the way, so if I rewind the way that we have included the common sense relations, right? So in that case, we are not enriching the graph with more observational data. We are enriching the graph with common sense relations that are available, for in general terms. But we basically see what is relevant with respect to driving and then integrate them, right? So similarly, if there's, let's say, driving rules that we want to integrate, if there's a way that we can gather what are the, safe driving rules, safe driving behaviors, and if there's a way to gather and represent them alongside the other observational data, yes, that will be helpful. But the one thing I want to highlight is, since the way that we have represented the scenes, it allows us to integrate these additional semantic information. Okay. So we have already demonstrated with two types of additional information, which is location, geospatial knowledge, and the common sense. But there could be a lot more out there that we can integrate with.
And then related to again, Professor Tiru, a question from the audience. Do you have any kind of explicit representation of statistics or probabilities or anything like that in your system?
Right now, we have not used. Right now, we have not used. No.
Thank you.
Yeah, thanks.
Okay. These are still general questions.
I just want to follow up on what Dr. Prasad said. Talking about the ball, the importance to the dynamic.
Yes.
I think maybe the reason we care about the ball is because of the severe outcomes that could go about if we ignore the ball. That's in the scene, right? The risk factor of not detecting the context around the ball, right?
Yeah.
Hitting a child. Detrimental.
Yeah.
So something chooses maybe use that answer to the
Yes. So I don't know whether you heard Corey's comment, Dr. Prasad. So what he's saying is that
yeah, can you repeat his comment actually?
Yes, I'll summarize. So what he's saying is that why did we focus on the ball in the original problem that you asked is because if we did not detect a child there, that could cause an accident. So the effect of not detecting the ball is detrimental. So the risk factor that is associated with not is higher than anything else. So one thing is, if I want to dig a little deep here, So that's why I think it is important we do an analysis based on also the entity types as well. So in current data sets, the data set that we use, they are not built for entity prediction. They are built for like visual reasoning, semantic segmentation, and object detection. But as a starting point, we had to use uh, those data sets. But if there could be a resource that we can isolate, let's say accident-prone scenes, the scenes near school zones where those kind of accidents are reported. So in that case, actually, we can dig a little deep and identify what are the important dynamic aspects of the scenes that we focus on. Yes.
Yeah, so I think continuing on that, right? So what I was suggesting was that this risk assessment will bring human in the loop. But I was wondering whether anomaly detection will reduce the scope of things that a human being has to inspect. Because the ball is not a common thing to appear in a scene involving, say, roads and cars, except when you are in the vicinity of say, some residential neighborhood. So
I would argue that this kind of framework is perfect for human in the loop, because if I remind the way that the current the prediction setup is structured, right? So we are asking the models to give us like top K plausible answers, right? So highest being the highest plausible answer. So it's basically like narrowing down the search space for humans to pick and choose. Yeah.
Okay, makes sense.
Thanks. Sorry, I didn't. Can you clarify? No, we have not. We are only dealing with real world data here. We are not using any simulated data for this work. Thanks. Okay.
So is it possible to use the generative AI to create such a data? Like, do we have any kind of knowledge source using which we can create actions which are very just captions of those situations, those rare
So I did briefly look up that line of work. So there's one particular simulator called like Kala. It's a driving simulator. So there are some follow-up works. People use the Kala to generate the visual scenes, but these are not real scenes. These are simulated scenes, and then use a generative AI framework. So take the visual scenes that are generated by Kala and then generate textual descriptions. So there's an active research area called like scenario generation. So basically you would specify what is the scenario that you want, and then it would generate some synthetic video as well as some descriptions. Yeah. Yes. Yeah. That's one active field scenario generation. Yeah. So I have recently seen that the knowledge graph that we built is used for one of the scenario generation paper as well. But at that example, they are still using it to bring the global context. Yeah. Thanks.
To make it completely clear, following up this question. So you say that this particular work of scenario generation that you mentioned actually exploited your own work on knowledge graph?
Yeah.
Thank you.
Yeah.
Questions from the audience here? Anything from online again? Maybe from non-committee members?
Okay.
Doesn't seem to be anything. So maybe this is the time to ask the audience to leave and just leave the committee here.
Thank you everyone who joined online.